Welcome to another mythology video. Picture this. You're deep in the woods, armed with nothing but your trusty battle axe and a burning sense of purpose. To rid the land of the ancient evil that has haunted it for generations. That 2D monster over there, flat and fearsome. Luckily, you know what to do. You have to calculate the area of the monster with your axe. For this, you jam the axe handle down near the center of the beast, like that. And you mark where the blade hits the ground. And then you trace the monster with the handle, center to edge. Okay. Once around the edge. So going, 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 going. Then back to the center. Mark the blade's new spot. Now to find the area of the monster and to finish it off, you just have to multiply the distance between the marks, about 5 centimeters, and the distance from the handle to the blade, about 80 centimeters. 5 times 80, 400 centimeters squared, you declare. The moment the monster hears its true area revealed, it crumbles into dust. And peace returns to the land. You are hailed as a hero, you marry the princess, and yes, you live happily ever after. Now, just in case you're wondering, no, this way of calculating the area of plane shapes is not a fairy tale. This works for any shape. Again, start with the handle near the center and mark where the blade touches. Move to the edge, trace around and return to the center, put another blade mark, multiply blade to handle length by mark distance, voila, the area. Well, at least roughly. Considering it's me doing the tracing with all the precision of a caffeinated squirrel, so you probably weren't expecting an exact value anyway, right? Now, just like an axe, the so-called hatchet planimeter up there has a blade at one end and a tracer at the other. Surveyors and engineers use these to quickly estimate areas of everything from land plots to mechanical parts. If you're keen to give this a try yourself, but don't have a hatchet planimeter or an axe at hand, don't worry, you can repurpose all sorts of things. A pocket knife works well, or a bent wire, one end flattened into the blade, or if you're the proud owner of a penny farthing, that works too. At the same time hatchet planimeters were in use, closely related precision planimeters were also used. Instruments that, at least in theory, let you measure the exact area of any plane shape. Here's one I picked up on eBay a while ago. Let's trace the circle to see how this planimeter works. Unlike before, we don't start in the middle, we simply trace around the shape. All right, here's a bit of common terminology I'll be using for the different types of planimeters we'll encounter. The red point, that's the tracer. I'll call the black segment the arm, and this is the constraint. Why constraint? Well, in the case of the axe, this point can only slide in the direction of the blade, right? It's constrained to that direction. In the case of this planimeter, this point is constrained to move along a circle. With center, the pole, there, moving along a circle. This type of planimeter is called a polar planimeter. In the case of our axe planimeter, we find the area by multiplying the length of the arm by the distance between where the constraint begins and where it ends. But in the polar planimeter, the constraint starts and ends at the same spot. So clearly, that won't work here. Actually, in this planimeter, the second distance is recorded by a wheel that is attached at right angles to the arm. This wheel both rolls and slips depending on how the tracer moves. Take a look. Do you see? The more the tracer moves along the direction of the arm, the more the wheel just slips and the slower it rotates. Let's take another look. There's quite a bit of slipping there, more slipping there. Nifty, huh? Let's call the total distance traveled by the wheel the roll. Then it turns out that the area of the shape is equal to the length of the arm times this roll. Exactly. Pretty amazing, isn't it? Now before we move on, let's take another close look at what's going on here. First, with planimeters, the convention is to trace shapes in the clockwise direction. That's different from maths, where the counterclockwise direction is the default tracing direction. Now, let's observe how exactly the roll is recorded. Okay, so let's roll. That was the wheel turning 180 degrees in the clockwise direction, or in terms of distance traveled, half the circumference of the wheel counted positive. Okay, here the wheel was spinning in the opposite direction, again 180 degrees, and since in this case the distance traveled is counted negative, the total distance traveled so far is 0. Roll again. Okay, again back to positive half the circumference of the wheel traveled, and finished. The final tally, about plus 0.7 of the wheel's circumference. Multiply that by the length of the arm and boom, there's your circle's area. Cool, huh? Now, unlike what you'd expect, in the real instrument, the wheel is actually not attached at the tracer but close to the constraint. There, that little white smudge there, that's the wheel. The placement of the wheel is a bit mysterious, but as we'll see, it does not matter where exactly the wheel is mounted as long as it's perpendicular to the arm. Case in point, here's the wheel mounted halfway along the arm. Trace again, and we get the same roll as before. Wonderful. Oh, before I forget, the Mathematica animation I just showed you is my adaptation of a piece of code originally put together by Stan Wagon for his book Mathematica in Action. If you're into maths visuals, you'll love this book. Links in the description. Alright, it's definitely quite miraculous that you can measure the area of a shape by tracing its edge, right? Think about it. For starters, there are lots of shapes that have the same perimeter and yet totally different areas, like those rectangles over there, right? Same perimeter, different areas, yet the planimeter still gets it right. So what's going on? How does tracing the edge reveal what's inside? Well, my mission today is to explain this miracle. Beautiful, beautiful stuff, promise. But before we hit the maths, let's take a quick stroll through history. Planimeters were heavily used from the mid-19th to the late 20th century by engineers, surveyors and scientists, until digital tools took over in the 1990s. The by far most popular type of planimeter were these polar planimeters. They're in action. This is a linear planimeter in which the constraint moves along the blue straight line instead of along a circle. This is a specialized planimeter for performing integration. That's another really fancy one, a so-called moment planimeter. It's got 3 separate wheels attached at specific angles, and apart from measuring area, it also allows to calculate things like the center of mass of a shape. Now, these are digitally enhanced polar and linear planimeters produced by the Huff company in Germany, the same people who also built my purely analog polar planimeter. According to the company's website, they still sell these digitally enhanced planimeters. They cost around 1,000 euros each. Ooh. In theory, it's even possible to play this planimeter game on a sphere. However, I'm not sure whether any physical sphere planimeters have ever been built. Here's a truly amazing book from 1951, all about mechanical maths machines. About a third of it is devoted to the countless types of planimeters made over the years. Makes for absolutely fascinating reading. Now, a modern day planimeter is an app that allows you to calculate distances and areas, for example, on a map on your phone by placing a couple of markers. Definitely also worth checking out. As usual here on Mathologer, the aim is to present the essence of whatever maths we're talking about in the most intuitive way possible. And of course, I'll also do that today with planimeter maths. But just to demonstrate what's often considered a great explanation and to highlight how much further one can go in terms of accessibility and clarity with a bit of effort, let me start by showing you how the planimeter is commonly explained using some fancy calculus weapon called Green's theorem. Don't worry if you don't understand everything I'll say, just try to glimpse some bits of insight here and there, enjoy the mathematical fireworks and the dad jokes, and bide your time for the super accessible part of today's video. Okay, so let me prove that the polar planimeter does what I claim it does in the special case of a polar planimeter, both of whose straight parts are of equal lengths. For that, we consider this planimeter's unit vector field. Here the vector arrow f of x and y is always perpendicular to the arm when we move the tracer to the point xy, like this. See how that little arrow sticking out at the tracer is at right angles to the arm? Same here and everywhere else. Now, by just torturing Pythagoras a little bit, we can figure out that f of x and y is equal to this monstrosity. Easy peasy, promise, really not hard. All right, here's the wheel. And here's the curve that we want to trace. Remember, we are tracing in the clockwise direction. All right, now let's zoom in on an infinitesimal part of this picture. There, as in the vector field, the orange vector is perpendicular to the arm, and the infinitesimal red vector is part of the curve. Now, as we trace along the red curve, the distance recorded by the wheel is this green distance here, right? The wheel acts like a directional sensor. It only feels motion that's perpendicular to the arm. But it slips when the motion is along the arm. Now, as all the real maths demons among you will know, the green distance is just the dot product of our two vectors. Don't know what a dot product is? Don't worry. All right, back to the big picture. Add up all those green infinitesimal specks a la calculus and boom, again, there's your roll. Hang in there, almost done. Enter Green's theorem, that slick trick I mentioned earlier. It lets us trade that fancy integral up there for a double integral over the region we're enclosing. What more scary integral signs, not fewer? Why on earth would anyone want to do that? Well, just like in a mathematical fairy tale, the curl of our Frankenstein vector field turns into a mathematical prince, a nice round constant number. And as usual, we can pull that constant in front of the integrals. And what's the value of that simplest of all double integrals up there? Well, in fairy tale language, that's just the enchanted area held tight within the curve's embrace. And there you have it. Area equals arm times roll, QED. Definitely a very slick proof and a great exercise for students who've just learned about Green's theorem. Yes. But this proof probably doesn't quite cut it when the aim is to explain the planimeter magic to a 10-year-old. Well, the whole thing becomes a little easier when we consider a linear planimeter instead of a polar planimeter where the constraint scoots along the y-axis. In particular, vector field becomes much simpler. Anyway, we still need something a lot more accessible for our primary school audience. Okay, here's the arm of a planimeter. First, let's attach the wheel in the middle. Here's a nice visual way to associate what the wheel records with some area. Positive area if the segment moves this way, okay, and negative area if we're moving in the opposite direction. Let me show you. Okay, let's roll a bit, just straight down, nothing fancy. Then obviously the red swept area by the arm is just the length of the arm times this roll distance here. So, if the curve we are tracing includes a translation like this, then the contribution of this translation to the final value of arm times roll is just this red swept area. In other words, as far as this translation is concerned, area really equals arm times roll. Clear, right? Also very important, as far as this translation is concerned, it clearly does not matter where the wheel is located. As long as it is mounted at right angles to the arm, as we translate, the wheel will always record the same. Okay, going in the opposite direction we get negative area, arm times roll distance again. All right, moving the arm sideways, the wheel does not record anything. No area is contributed by a motion like this. Works. Now let's translate at an angle. Area of a parallelogram, that's space times height. And of course, the height here is exactly the roll distance. Works. In fact, I think it's pretty clear that this will work for any motion in which the arm is just translated around. Now, for motions more complicated than pure translations, this won't necessarily hold. But let's postpone figuring out what happens in those cases. For now, it's enough to know that when the motion is a translation, it contributes to the final arm times roll value as swept area. And that, in this special case, the wheel's position along the arm doesn't matter. All right, have a look at this rectangle. Let's use a linear planimeter whose constraint is moving along a line to figure out what exactly arm times roll is for this simple setup. Now, the wheel could be here, or there, or there, or anywhere else along the arm. For the moment, we won't worry about where exactly. Ready to go? Okay, so let's trace the rectangle. First, straight up. That's a translation of the arm, and so this is the area contributed to the final arm times roll result. Okay, now across to the right. Okay. That's quite a complicated motion as far as our arm is concerned. Not sure what the wheel does there, but again, let's not worry about that for the moment. Now, move straight down. Well, that's another translation, and the area contributed to the final result is this. Okay. Now, back to the start. All right, can you see where I'm going with this? No? Well, the motion of the arm just now is the exact opposite of the one at the top. This means that whatever the wheel recorded at the top was just cancelled out again here at the bottom. How neat is that? And that means that the final arm times roll is equal to this parallelogram area, which is equal to this, plus this. And since the blue area counts negative, this sum is exactly equal to the area of the rectangle. Victory! At least in the case of this rectangle, in our linear planimeter, we've just convinced ourselves that area equals arm times roll. And because only the translation contributed to the final result, we also conclude that the exact position of the wheel is irrelevant for this to be true. Nice argument, isn't it? Well, yes, but what about more general shapes? Well, how about this one? A compound of 4 rectangles. How can we measure the area of this compound shape with our linear planimeter? Easy. Just trace the 4 rectangles one after the other and add up the resulting areas. Yes, but how does that help? Well, take a look at the common boundary of the 2 rectangles on the left there. Now, as we trace the little rectangle on the far left, there, moving down, the following area gets recorded as we trace across the common boundary. Okay, now, as we trace around the middle rectangle, there, now as we move up across the common boundary, we're moving in the opposite direction. So the recorded area is the negative of the one before. And so these 2 areas cancel each other out. There, zap! The same sort of cancelling also happens for all the other common boundaries. And that means that we may as well remove all these common boundaries and just trace around the shape to get its area. Neat, 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 neat. Finally, any reasonable shape can be approximated arbitrarily well with rectangles, and so at least intuitively, it's now clear why our linear planimeter always works as advertised. Anyway, all very cool, don't you think? Even cooler, it turns out that the arguments here can be easily modified to give the same result for polar planimeters. Too nice to skip, and so let me also show you how that works. Translate a copy of the arm over here. Now do this. Ta, 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 ta. The curvy rectangles that can be constructed like this can replace the real rectangles in the proof just now. Have a look. Tracing up, that's a straight rotation. Since we have not specified where the wheel is, we don't know what exactly is recorded here. Now comes a translation that hugs the circle, and so the area contributed is this. Now another rotation. Whatever is recorded here just cancels out what was recorded during the rotation earlier. Now, another translation that hugs the circle. All right, so that means that the arm times roll is equal to that red area over there plus the blue area. And this is the same as this red area plus the negative blue area, which is the area of the curvy rectangle again. Perfect. exactly what we want. And now compound shapes, you can remove common boundaries for the same reason as before. And finally note that any shape can be approximated arbitrarily well with these compound shapes. What a magical argument, don't you think? But there's still one piece of the puzzle I haven't explained, the X magic. And as it turns out, what we've covered so far won't quite get us there. For that, we need to dig a little bit deeper. All right, let's trace the rectangle one more time with our linear planimeter. Again, with those parts of the trace that are translations, the area contribution recorded by the wheel is just the swept area. Well, maybe the sweeping area business is also worth considering for the more complicated parts of the trace, like this one. During this movement, the arm does not only translate, but it also rotates. Let's take a closer look at how area is swept when the arm rotates. There. So the swept area of the arm is partly positive and partly negative. Back to tracing our rectangle. On close inspection, during this complicated movement, we also have a mix of positive and negative areas being swept. There. That's all positive area, and this is negative area. There's an overlap where positive and negative cancel out, and so the swept area is really this. Tracing down, we get more no-brainer swept areas before, and then we get the same swept areas at the top, just with signs reversed. Things cancel out again at the top and at the bottom, but then we don't really know how in general those complicated swept bits relate to what the wheel records when it's fixed at different positions along the arm. And so, is considering the total swept area actually useful? Not clear at this point, but let's continue undeterred. Take a look at this. So we trace both curves simultaneously in the clockwise direction. Our red tracer travels around the red curve and our blue constraint travels around the blue curve. Now, here's what happens in terms of swept area. Interesting. So the regions enclosed by our two curves are swept once each, and some bits outside are swept twice. Let's take another close look at what happens here in terms of positive and negative area. There. That swept area is positive, 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 negative, 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 positive, 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 positive. Okay, so the area enclosed by the red curve counts positive, and the area enclosed by the blue curve counts negative. And the remaining swept area is swept once in the positive direction and once in the negative direction, leading to overall cancellation of the swept area there. This means that the total sign swept area is just the sum of the red positive area and the blue negative area. And of course, here T and C stand for tracer and constraint. Anyway, very cool, We're definitely onto something. What's even cooler is that this stays true in general, as long as the two curves are side by side and the two ends of the segment move once around these curves in the clockwise direction and return to their original positions, this will work. This will work even if the curves and the movement of the segment are a lot crazier than those up there. For example, like this. After we account for all the overlaps of positive and negative swept area, we get the same picture and identity as before. Even better, it turns out the swept area is always arm times roll, and that the position of the wheel does not matter. Here's a quick way of seeing why this should be true, why the swept area should be arm times roll. Here are a couple of snapshots of the arm at the start of its movement. What's the swept area up to this point? Let's take a close look. We can approximate the motion of the arm by subsequent tiny translations and rotations like this. First translate, then rotate, translate, rotate, translate, rotate, and so on. This means that the total swept area is equal to the total translated area plus the total rotated area. Now, take a look at this. What's happening here? Well, as the sweeping on the left progresses, the animation on the right shows the total accumulated rotated area. At first, the arm rotates clockwise, adding positive red area, but when the direction of rotation reverses, blue area appears and cancels out the red. And so it continues, adding and subtracting. Also, in the end, the arm returns to its original position with a 0 net rotation, and so the total rotated area is also 0. Take another look. Okay, now comes the cancelling out, and now comes more cancelling out. Again, the total rotated area is 0. Haha, victory again! Very similar to our previous victories, where all that remains after the complicated bits cancel out is the translated total area, which is really just arm times roll, no matter where the wheel is fitted. Anyway, with a lot of hand waving, we've convinced ourselves that, in general, arm times roll is equal to the swept area, which, in turn, is equal to the red area plus blue area, no matter where the wheel is fixed. Fantastic! But now, with this formula at hand, we can explain everything, even how measuring area with an X works. Ready for the finale? Okay, first let's warm up with the linear planimeter again. In the case of a linear planimeter, the blue region degenerates to a line, which, of course, is of 0 area. And so we find again that the area of our shape is just arm times roll. Neat. And of course, exactly the same argument works for polar planimeters. In fact, the argument shows that if we have the constraint run along any sort of curve, not just lines and circles, this identity will hold. Now, finally, what about our X? Well, let's see. With the X, what's the blue curve that the constraint traces? Well, here we go. Interesting, our curve is not closed, and so our identity does not apply, at least not to start with. Well, don't worry about that for the moment. Imagine tracing the blue curve one more time with our X from the start to the end, but this time we attach the usual wheel in an unusual spot, right at the constraint, where the blade is touching the ground. Now, since the motion of the constraint is always along the blade, that is, perpendicular to the wheel, throughout its movement along the blue curve, the wheel is not turning at all. That's interesting, isn't it? Okay, now let's do something ingenious. Let's close the blue curve by rotating the X around the handle. Now our identity applies. Also, remember that the wheel did not turn at all before, and so that means that the roll in our identity is just the length of the circular arc that we just added. That's the only part where the wheel turns, right? Aha! Now it's all starting to make sense, right? Remember what I measured in the fairy tale part of this video? Was the straight line distance between those 2 points. And of course that straight line distance is a good approximation for the length of our shallow circular arc. So, multiplying the length of the X by the distance between the marks to approximate the swept area is definitely a reasonable thing to do. Yes, but what about the right side of our identity? We want that right side to be just that red area, right? Unfortunately, there's definitely some blue bits and pieces that we have to worry about. And so what is that blue area? Well, after all the cancelling out of the overlaps, what remains is this. What a surprise! We end up with a mix of red and blue areas that partly cancel out, leaving a result not too far away from 0. Aha! So that's why the planimeter works. Okay, but where does this mix of red and blue areas come from? Well, on close inspection it all boils down to the blue curve folding over itself, causing different tracing directions around the 3 individual pointy regions. Have a look. 2 of the 3 regions are traced clockwise as usual, resulting in negative area, and 1 is traced in the counterclockwise direction, resulting in positive area. There, blue arrows clockwise and red arrows counterclockwise. Well, there are plenty more curious details to unpack here. But the key takeaway is this. While linear and polar planimeters measure area exactly, the X planimeter just gives an approximation. So, why use it at all? Well, for one, it's cheap and virtually indestructible, unlike its pricier, much more delicate cousins, and despite giving only approximation, the explanimeter can deliver surprisingly good results. And that brings us to one more special feature of the explanimeter, the fact that we're starting the tracing inside the red curve and not on the curve. Well, we start inside to make sure that we get those convenient cancelling areas, making area C close to 0. Just to compare, let me show you what happens if we actually start with the tracer on the curve. So the blue curve no longer folds over itself, so no more cancelling bits, resulting in a huge error. Alright, so finally, where then is the best spot inside the curve to start the trace? Well, a detailed analysis reveals that starting at the center of mass ensures that those pesky cancellation areas really do balance out as neatly as possible. Problem solved! Except that pinning down that exact center of mass is at least as hard as finding the area of the curve. But then, close enough is good enough. Definitely as far as our explanimeter is concerned. Alright, the explanation using the complete swept area that I presented in this chapter definitely gives the most insight into what's going on with planimeters in general. At the same time, this explanation is much more hand-wavy than the explanations presented in previous chapters. If you're interested in the gory details plus some amazing 3D counterparts, check out the links in the description. In particular, check out that textbook by mathematical superstar Richard Courant over there. This textbook appears to be the original source for making very visual sense of all the planimeter magic using the total swept area. To finish off, let me show you something cute. Again, it's our X in action, but this time it's sweeping out this red ring, as usual in the clockwise direction. What's the area of this ring? Prior to watching this video, a tricky question, but now easy peasy, right? As before, this formula applies. However, as in the case of the explanimeter motion, the wheel fixed at the blade end would not turn at all throughout the tracing, and so the total translated area must be 0. Nifty. And here's the total rotated area. And so the area of the ring is equal to the area of that circle. Quite a pleasant surprise, don't you think? And of course the same is true for any ring like that. In particular, it's true for all circular rings. But it also means that all circular rings with the same length in a chord have the same area. All of these have the same area. There, all of these. All super nice. And in fact, this is the starting point for a beautiful theory of doing calculus without actually doing calculus. Beautifully explained in this remarkable book over there. On my to-do list for another video. Anyway, that's it for today. Except for one final challenge for you. Take a look at this. What's the red area under the blue curve? Share your answers in the comments below. And so, until next time, take care.